Welcome to this fascinating two-part compilation exploring Flinders Island, a remarkable gem tucked between Tasmania and Victoria in Australia. This island is home to an astonishing gemstone known as the Killiecrankie Diamond, which so closely resembles true diamonds that even early gemologists were baffled by them. In the first part, we'll dive into the captivating story of the Killiecrankie Diamonds, their unique characteristics, and the geology behind their erosion from the island's granite foundations. In the second part, we'll embark on a comprehensive journey through the geological history of Flinders Island, tracing its transformation from a deep-sea environment 500 million years ago to the stunning landmass that rises above the waves today. I hope you enjoy this deep dive into the natural wonders and geological marvels of Flinders Island.
Check this out. It looks like a diamond, doesn't it? But looks can be deceiving. This is the story of the so-called Killiecrankie Diamond, a gemstone found on Flinders Island, located in the Bass Strait between Tasmania and Victoria. These gems were among Australia's earliest gemstone exports in the early 1800s, and their high hardness and luster make them durable and visually appealing, and when faceted, they sparkle in a way reminiscent of diamonds. But spoiler alert, they aren't diamonds. The Killiecrankie Diamond is a form of brilliant white topaz, known for its exceptional clarity, high refractive index and hardness, which give it a sparkling diamond-like appearance. This topaz is often colourless and transparent, qualities that resemble those of true diamonds, leading early settlers and collectors to mistake it for the real thing. The topaz is primarily found on Flinders Island, concentrated at the northeastern end of Killiecrankie Bay on the island's northwestern coast. It also occurs commonly on nearby Mount Killiecrankie in offshore sediments and in Mines Creek and Tanners Bay, located approximately 10 kilometres to the south. Alongside this, the topaz also occurs on Cape Barren Island to the south of Flinders Island. Although these findings took on the name of Cape Barren Diamonds, these topaz deposits share the same geological origin as the ones found on Flinders Island, which we will discuss soon. Flinders Island is associated with tin mining activity, though most of the mining actually occurred on nearby Cape Barren Island. Both the tin and topaz found in the region originate from granite formations. The first export of topaz definitely occurred before tin mining began. The tin mineral cassiterite, found in association with the topaz, had not yet been identified at the time. Tin mining began around 1882, but the first discovery of Killiecrankie diamonds likely occurred as early as 1803 according to studies done on it. In 1851, a remarkable collection of Killiecrankie gemstones made its way from the remote shores of Flinders Island to the Grand Crystal Palace in Hyde Park, London. This display, part of a grand exhibition showcasing the treasures of the British Empire, included a variety of topaz crystals collected by Joseph Milligan and his team. While these gemstones had become known as Killiecrankie diamonds due to their sparkling clarity, the exhibit revealed an array of colours beyond the classic clear or white stones. Among the 300 white topaz specimens, viewers marvelled at 40 yellow and 30 pink topaz crystals. Alongside the topaz, Milligan's team had gathered other gems, including 25 pieces of rock crystal and 30 beryls, all part of this fascinating display that showcased the mineral wealth of Australia's Flinders Island and drew admiration from audiences halfway across the world. To clarify, rock crystal is a term used for colourless transparent quartz, also more commonly known as quartz crystals. Beryl is also found on the island, and it is best known as the family of gemstones that include emerald, aquamarine, morganite, and heliodor. Based on the source from Mineral Resources Tasmania, it appears that the beryl found on Flinders Island includes both colourless goshenite and bluish-green aquamarine varieties, though it is typically not gem quality. Now, this topaz is associated with a few controversies dating back to at least the 1850s, when an attempt was made to sell it off as diamonds in the UK. According to old articles from that time, attempts were made to sell off Cape Barren topaz as diamonds. The seller fully believed that they were diamonds, and even the London lapidary, whom he sent specimens to be tested, believed that they were quote diamonds but of no value. A second person was given the topaz specimens to test. He immediately said that they were not diamonds and were soft, but upon attempting to file it down, he was surprised by how hard the specimens were. He couldn't make up his mind on what these rocks were. The defendant was later acquitted due to the fact that no one could agree on what these gemstones actually were, and it was decided that he wasn't attempting to scam people, but that he really believed that the topaz gems were in fact diamonds. Another controversy occurred in 1919, this time with Killiecrankie diamonds. Unlike the 1850s, at this point in time, testing for gemstones had advanced to the extent that scientists could distinguish between crystal systems and identify minerals based on their crystal habit and symmetry. By analysing characteristics like cleavage, hardness, and crystal shape, gemologists were able to determine that the Killiecrankie topaz exhibited an orthorhombic crystal system rather than an isometric or cubic crystal system typical of diamonds, which commonly display dodecahedral or octahedral habits. These visual and structural differences, along with the evolving field of X-ray crystallography, allowed experts to more accurately classify and authenticate gemstones, reducing the risk of misidentification. Alongside this, it was noted that none of the specimens scratched a diamond, a telltale sign of topaz's lower hardness. While diamonds rank at 10 on the Mohs scale, making them the hardest natural material, topaz has a hardness of 8, which, although durable, is not sufficient to scratch a diamond. This hardness test provided a straightforward and effective method for confirming that the so-called Killiecrankie diamonds were in fact topaz, despite their similar appearance and sparkle. But this isn't all. By 1919, the geology of diamond fields had been more thoroughly established thanks to the African diamond rush in South Africa. Geologists knew that ultramafic rocks, specifically kimberlite, hosted diamonds, and that not a single trace of this rock existed in or around Flinders Island, which is composed of sediments and granites. So where did these beautiful topaz gemstones come from? Well, from the ancient magma that now exists as solidified granite on the island. Flinders Island hosts a variety of granite formations ranging from the Devonian to Carboniferous periods, spanning from 419 to 299 million years ago. It contains both S-type and I-type granites, with each contributing differently to the island's mineralogy and gem potential. To clarify the difference between I-type and S-type granites, I-type means igneous type granites, while S-type means sedimentary type granites. S-type granites, such as the Killiecrankie, Cape Franklin, Babel Island, Strzelecki and Lady Baron granites, contain aluminium-rich minerals due to their origin from the melting of sedimentary rocks like clay and shale. These granites are rich in minerals like muscovite, garnet and biotite, and the high aluminium content fosters the formation of gemstone-quality minerals such as the topaz. In contrast, I-type granites, including the Polana, Lagrada, and Darling Range granites, originate from the melting of igneous rocks with lower aluminium and higher calcium and sodium content. I-type granites are characterised by a different mix of minerals, often containing higher amounts of mafic minerals such as hornblende. Although both I-type and S-type granites can include biotite, the S-types are typically richer in aluminium. This higher aluminium content in S-type granites make them more conducive to forming aluminium-rich gemstones, like topaz. The difference between these two types is significant for the gem landscape of Flinders Island. While I-type granites add mineral diversity with common minerals like quartz and feldspar, the S-type granites provide the prized gem deposits that have made Flinders Island an attractive destination for gem collectors. The I-type and S-type granites on Flinders Island form through distinct geological processes, each resulting in unique mineral compositions and characteristics. I-type granites originated from the partial melting of mafic igneous rocks, likely in a subduction-related tectonic environment during the Devonian. This process involved the melting of basaltic or andesitic rocks, producing a magma rich in calcium, sodium, and iron, but lower in aluminium. As a result, I-type granites are typically a denser, darker appearance with fewer aluminium-rich minerals. I-type granites typically cool and crystallize at a moderate rate within the crust, which can limit the growth of large crystals compared to the slow-cooling pegmatitic pockets often found in S-type granites. While they can form pegmatites, I-type granite tends to contain standard rock-forming minerals such as feldspar, quartz and biotite, rather than the rare or gem-quality minerals commonly associated with S-type granites. In contrast, S-type granites on Flinders Island formed from the partial melting of aluminium-rich sedimentary rocks, such as shales and claystones, in a deep crustal setting. This type of granite is derived from sedimentary sources, resulting in an aluminium-rich, silica-saturated magma that crystallized into granites containing minerals like muscovite, biotite, garnet, and occasionally tourmaline or cordierite. The presence of volatiles, such as water and fluorine, in the late stages of granite crystallization allows for the formation of pegmatitic pockets. Pegmatitic pockets within granite are small, mineral-rich zones found in coarse-grained igneous rocks, particularly granites. These pockets form during the final stages of magma crystallization, when the magma chambers finally reach the point of near-complete solidification from magma to rock. volatile elements like water and fluorine become concentrated, lowering the magma's viscosity and allowing large, well-formed crystals to grow. This slow-cooling, mineral-rich environment within the pockets provides ideal conditions for forming rare and high-quality minerals such as topaz. The main topaz deposit is found in cavities within granitic pegmatite veins. These pegmatite veins, which can reach widths of over a metre, contain well-formed, free-growing crystals of topaz along with quartz, schorl, beryl and feldspar, with some crystals measuring over a metre in size. Individual topaz crystals are often collected from eroded pegmatite pockets around the bay, where they occur alongside smoky quartz, large mica books and feldspar crystals. However, retrieving intact matrix specimens is challenging because topaz, which crystallizes late in the sequence, detaches from cavity walls due to the decomposition of surrounding feldspar and its own cleavage properties. In the case of topaz on Flinders Island, these pegmatitic pockets within the Devonian Killiecrankie granite intrusion, shown here, provided the necessary aluminium and fluorine-rich conditions for topaz to crystallize. Over time, erosion exposed these pegmatitic pockets, releasing gem-quality topaz crystals into alluvial deposits where they could be collected. Most of the topaz recovered today is from recent alluvial and residual deposits, including some offshore areas. Richer alluvial deposits containing both cassiterite and abundant topaz are also located south of Tanners Bay. To the north of Killiecrankie, blue beryl or aquamarine has been reported in some abundance. So this is the truth about diamonds on Flinders Island. They aren't really diamonds, but they definitely look like it. Even though they aren't real diamonds, they are a beautiful and fascinating variety of colourless topaz. With their brilliant clarity and diamond-like sparkle, these gems have captivated collectors and fossickers for centuries, adding a touch of mystery and allure to the island's rugged landscape. Today, fossickers are still allowed in the area to hunt for their own beautiful topaz specimens, and I definitely suggest giving it a go if you ever find yourself able to journey to this fascinating island. I hope you found this topic to be as interesting as I did, and as always, thanks for watching. Geology is a fascinating science. We get to understand how the world formed, how islands were uplifted from deep seas, and how tectonic events shape the landscapes around us. Flinders Island is a perfect example, a place with a geological history that tells the story of ancient seas, volcanic eruptions, and the uplift that occurred during massive mountain building events which thrust the land up from the deep sea. From the crystalline granite intrusions of its mountainous regions to the limestone deposits from former shallow seas, Flinders Island's geological construction offers a unique glimpse into Earth's dynamic past. Let's explore how these forces came together to create the island's rugged beauty and mineral diversity, revealing the secrets of its formation across hundreds of millions of years. Flinders Island is located very close to Tasmania. Western Tasmania is part of an ancient microcontinent known as Van Dieland. Notice I say Western Tasmania, and this is for a good reason. In a future video, I will cover the collision and joining of the east and west of Tasmania, which occurred during the Devonian. Be sure to subscribe if that interests you. Western Tasmania contains rocks that are around 1.6 billion years old. It's had quite a significant journey through time before it collided with Australia between 500 to 430 million years ago. It has connections to Antarctica and even North America. In fact, it was the erosion from both of these landmasses that led to its initial construction. I've already made an episode on that and on the geological construction of Tasmania, and you can find both of those videos in the description below. Tasmania and King Island have both existed for the same period of time, but Flinders Island is much younger. During Ordovician, 485 million to 444 million years ago, Flinders Island was submerged beneath a deep ancient sea, as indicated by deposits of the Mathinna Supergroup, which consists of marine turbidites made up of mudstone and micaceous quartz wacke. These sediments were laid down on the seafloor, showing that the region was once a deep marine environment. So what are turbidites? Well, underwater landslides leading to turbidite formation typically begin with sediment accumulation on a continental shelf, where layers of mud, sand and other materials build up over time. As the sediment layers thicken, they become increasingly unstable, particularly during events such as earthquakes, storms or rapid sediment loading. This is a present-day continental shelf. Material from rivers carries sediment to the ocean. This sediment can accumulate on the shelf, and then, boom, submarine landslide and turbidite deposits occur. These triggers can cause the sediment to suddenly collapse and flow down the continental slope as a dense, fast-moving turbidity current. The current sweeps the sediment into deeper ocean basins, where the particles settle out by size. Coarser grains like sand drop first, while finer mud and silt settle later, creating the graded bedding characteristic of turbidites. Turbidity currents can travel impressive distances, ranging from tens to hundreds of kilometres in more localised events, up to 1,500 kilometres for larger flows, and even exceeding 3,000 kilometres in extreme cases. The extensive turbidite deposits of the Mathinna Supergroup on Flinders Island reveal a history of repeated, far-reaching underwater flow events, preserving a record of deep marine processes that shaped this region during the Ordovician. The turbidites continued to be deposited through the Silurian period, 444 to 419 million years ago, and into the early Devonian, 419 to 393 million years ago. And after that, well, it's uplift time, and it begins with the Tabaraba and orogeny. The Tabaraba and orogeny, occurring during the Middle Devonian around 385 to 380 million years ago, was a brief yet intense tectonic event that reshaped southeastern Australia, affecting regions in Victoria, New South Wales and Tasmania. Driven by tectonic compression along the eastern edge of Gondwana, this orogeny caused widespread folding, faulting, uplift and crustal thickening. The compression generated enough heat to partially melt the crust, resulting in significant granite intrusions that are visible today due to later uplift and erosion. This event marked a major transition, ending marine sedimentation and uplifting previously submerged regions above sea level, subjecting them to erosion and forming rugged landscapes. And it's likely that along with being uplifted from the deep sea, Flinders Island's first glimpse at subaerial life involved the development of a mountain range, or at the very least an elevated terrain that has completely eroded today, unveiling the once deep granitic batholiths, which were previously vast deep magma chambers that never made it to the surface to erupt, and instead cooled and solidified, only to be later uplifted. They now dominate the islands in this region and the northeastern part of Tasmania. These granite batholiths were very deep in the earth when they formed, and their emergence to the surface occurred during something known as isostatic rebound. This is a process where the Earth's crust slowly rises or rebounds in response to the removal of weight from above, like the effects of erosion. Imagine a crust as a flexible block floating on a denser layer beneath. When heavy weight, such as mountains or thick layers of rock, is removed over millions of years, the crust responds by slowly lifting itself up to find a new balance, much like a sponge rising back up when you stop pressing on it. Over millions of years, erosion stripped away the upper layers of rock on Flinders Island. With this loss of mass, the crust underneath the island felt less pressure pushing it down. This removal of weight allowed the crust to slowly rise or rebound upward to balance out the loss. This gradual uplift helped expose the Devonian and Carboniferous granite batholiths that we see on the island today. While isostatic rebound didn't create dramatic mountains, it allowed the deep-seated granite to come even closer to the surface as layers above were eroded away. Even as the crust rebounded, erosion continued to wear down the surface, keeping a balance over millions of years. This combination of isostatic rebound and erosion eventually exposed the ancient rocks that were once buried many kilometres deep. So after the Tabaraba and orogeny ended, Flinders Island was uplifted and turbidite deposits ended. The region remained relatively stable for around 200 million years until the breakup of Gondwana occurred. During this time of relative stability, marked erosion of the former uplifted terrain occurred, and the granite began to be exposed to the surface. Gondwana began breaking apart during the Mesozoic era, with initial rifting between various landmasses starting around 180 million years ago in the Jurassic period. The separation that directly affected the area around Australia and Antarctica occurred later, in the Cretaceous period 145 million to 66 million years ago. The Tasman Sea began to form due to the rifting between Australia and Zealandia, a submerged continental fragment that includes New Zealand, during the late Cretaceous around 85 to 55 million years ago. This rifting extended into the Cenozoic, creating the Tasman Sea and contributing to the separation of Australia from Antarctica. Even though the Tabaraba and orogeny ended around 380 million years ago, the tectonic compression of the region didn't entirely cease. Instead, southeastern Australia, including Tasmania and areas like Flinders Island, remained under compressional forces for a long period afterward due to the ongoing plate convergence along the eastern edge of Gondwana. However, the rifting event changed these forces to extension, as Zealandia began pulling away from Australia. This shift from compression to extension marked the start of crustal thinning and stretching along the eastern margin of Gondwana. The change from compression to extension led to isostatic adjustments in the crust around Flinders Island. Isostatic adjustments refer to the slow, vertical movements of the Earth's crust as it seeks to maintain a balance with the denser layers below it. As Zealandia drifted further away, the crust beneath Flinders Island responded by flexing slightly upward due to the reduced tectonic pressure. This flexural adjustment or minor uplift wasn't dramatic but helped maintain the island's elevation as the surrounding crust adjusted to the new tectonic regime. During the Cenozoic, the period starting around 66 million years ago, Flinders Island experienced volcanic activity that was likely characterised by small scattered eruptions from fissures and vents rather than large sustained volcanic structures like stratovolcanoes. Evidence of felsic rhyolite, tuff and a variety of mafic to intermediate volcanic rocks suggests that the island saw explosive eruptions, with ash and pyroclastic materials spread across the landscape, and effusive lava flows, a type of eruption characterised by low explosivity that releases voluminous fast-flowing lava. However, the lack of large volcanic landforms implies that these eruptions produce smaller features. The magma source for the Cenozoic volcanic eruptions on and around Flinders Island is likely linked to the tectonic processes associated with the rifting of Zealandia and the opening of the Tasman Sea. This rifting would have left residual heat and weakened areas in the crust. These conditions allowed for localised volcanic activity to occur even millions of years after the initial rifting. When hot basaltic magma comes into contact with granite-rich continental crust, it transfers heat to the surrounding rocks, which can lead to partial melting of granitic material. This process can create a more silica-rich magma, like rhyolite or dacite, as the basaltic magma mixes or melts parts of the granite. In a study, there were several eruptive centres listed. There appears to be 2 locations where explosive eruptions occurred, which are listed here. Along with this, effusive eruption centres occurred in these locations. Finally, there also appears to have been a shallow sea that crossed over sections of the island. There are limestone deposits suggesting a shallow sea intruded into the island. There is a website that states the limestone near Tanner's Bay is related to sand dunes. Limestone can form from sand dunes when calcium carbonate particles, often from marine shells or coral fragments, accumulate and cement together within the dune environment. So parts of Flinders Island have been built up within the past 66 million years, likely as a result of the recent volcanism that occurred here. Today the island is primarily composed of sediments eroded from granite, along with limestone, sandstone and other sedimentary deposits that reflect its long geological history. These layers tell a story of ancient uplift, volcanic activity, and coastal processes that have shaped the island over millions of years, leaving behind rugged landscapes and unique mineral formations. So this is the geological story of Flinders Island, from a deep sea to a rugged landscape shaped by ancient tectonic forces, volcanic activity, and erosion over millions of years. Today, its exposed granites, limestone formations, and unique mineral deposits offer a glimpse into the dynamic processes that brought this island to life. I hope you found this video to be as interesting as I did. And as always, thanks for watching. Before I end this video, I'd like to give a big shout out to my Patreon and YouTube members. Thank you so much to everyone that helps to support this channel.